So my name is Edison Chan. I'm a year one PhD student of Dr. Anderson N. So I'm invited to give you this guest lecture today. All right. So everyone can hear me, right? Right? Clear? Okay. So as far as I know, so Anderson has told me that you have already learned like things like the combinatorics, right? You know how to count, right? So you know 1, 2, 3, 4, 5, right? All right, you know how to count. That's great. So this is for you. Um, okay, so today's our topic is about this, the counting problems involving symmetry. But we are not going to use the traditional combinatorics way to solve the problem. We're going to use a new perspective. So we'll make use of something called group theory. All right. So I don't know if you have heard of that or not. Whatever, doesn't matter. So this is for you guys. I mean, like, well, I assume no knowledge in the group theory, so it's okay. So let's just begin and find what's this about, right? Okay. So, all right. So this is the plan for today. All right. So I'm going to throw 3 problems for you. All right. 3 motivating problems, and they are all counting problems. And you could try to use your own method to solve it. I'm going to show you the VWAS thing to just have you guys have a wild guess on that. All right. But before this, let me tell you what those problems are. And I'm going to also show you a web app which I coded and show you how we can just attack those problems or understand that problem. Okay. All right. So those 3 problems are like this. The first one, okay, we are going to find how many distinct dies are there, all right, constructed by labeling 6 numbers on those 6 faces. You know what this means by a die, right? Yeah, it could. You can see that. All right, so we have 6 numbers, all right, and we can put the numbers on it, okay, and then we form a die, right? But how many distinct dies are there? That's the problem. Okay, the next one is we have 3 decks, poker decks, all right, and then we combine them, all right. So we have a very gigantic, like, just many cards there. It's a big deck, and we draw 3 cards out of it, okay, without replacement though, all right. So we draw those 3 cards at the same time, and so how many hands are there? That's the question, right? All right. The third one is how many distinct netnicks can be made using 2 black and 2 white beads? All right. This one may be easier. All right. You may be able to just tell me the answer right away. So by now, right? But okay, we can also make use of your theory to solve this problem. Actually, any of this, all these 3. Okay. And you can also see that, all right, these are counting problems, but when you count it, you have to be very careful. All right. Because you may overcount it, right? Because when you consider things like, well, for example, netness. This is the easiest one, right? So let's attack this one first. Okay, so we have 2 black beads, 2 white beads, and we can just arrange them, right? Like this. But now, I can also put those black beads like top and bottom, and those white beads like left and right, right? But they essentially giving me the same lattice, right? All right, that's the problem, right? So we have some symmetry there. All right, by some symmetry thing, we actually get the same thing by considering different arrangement, right? Okay, so let me show you a better way to understand what's going on with this. Maybe let's go to the netness first. All right, so like this. Okay, we can arrange those beads like this, right? But you can just rotate them. You have another arrangement, but they give you the same netness, right? Again, right? And even if you flat it, right? So you still get the same thing, right? Yeah, but you have different arrangement, right? So like the first 2, they are like black. The last 2, they are the white. But you can also do it another way, right? The first 2 are white, and the last 2 are black, but they're the same thing, right? and you change the type, then you can see that, well, now if you reflect it, you get the same thing. Actually, just that thing, right? But when you rotate it, you get another arrangement, right? So remember, different arrangement may give you the same thing. So when we count it, we have to take into considerations the symmetry, all right? And how about the cards? Let's look at this. So we have 3 decks combined, right? So altogether, 52 times 3, right? 156, right? Hope I'm correct. Okay, 156. All right, so now you can draw 3 cards from it. Okay, for example, you draw this, right? But, well, you note that when you draw it, you're drawing it from like 3 decks, right? So you actually could draw it in like different orders, but those different orders things will give you the same hand. Understand? Yeah. So just by permutations, you actually get the same thing. Though you're like, well, drawing it in different order, there seems to be a different hand, but they're actually the same hand, right? Yeah. So maybe you would also have some case like you draw the same thing. Okay, let me just see if I could get it. Well, come on, I'm out of luck. Well, I actually would like to show you if we have like 2 of them are the same. Oh, come on. Oh, yeah, finally we get this. Okay, yeah, so now you can see that. We could have a hand like this, right? Because we have 3 decks there, right? 3 decks. So there could be some situations we get like 3 cards there, they're all the same, right? 2 of them are the same, right? So like this. And we consider the permutations of them. Well, so you can see that actually some of them are like, this one and this one. They are actually the same order and same hand, right? Yeah, things get quite, weird and clumsy here now. Yeah. And more difficult is like dice, right? So now we have 6 numbers on 6 faces. Well, so when you put the numbers into it, and put the numbers on the faces, so you can get different numbers here, right? But like here we have the XYZ. XYZ is you know that this is the Y, and it's XYZ. We goes like this, all right? Anyway, so now when you put the numbers on the faces, but they may actually give you the same die, right? Because why? Hey, come on. If I put the numbers like this, we can actually just rotate it to get another arrangement. Cool? We have the x-axis, y-axis, z-axis. We can also do the diagonal, right? We have 4 diagonals there. Well, just come on. Lock it. All right, 4 diagonals, 4 diagonals. All right. And then we also have the edge centers. All right. So like, I don't know if you can see it. Like this, right? So you like flip it over, but the diagonal is just in the middle, right? Yeah, you have to have some like visualization in your mind anyway. But all right, so when you rotate it, you can see that, well, different arrangement can give us the same thing. All right, so now the next question is, well, we know the problems now, so how can we attack them? Okay, I tell you, we can use the group theory to attack them. Okay? So what is this about? So we have to know what is meant by a group first. Okay? So is anyone here or anyone in chat who know what a group is in mathematics? No. Right? Okay, I assume no, and it's okay. So let me just tell you the idea of, so what, I will give you the precise definitions, don't worry. But apart from the precise definition, I would like you to have an impression of what a group is, okay? So a group, actually, you can see it as a formalizations of the idea of symmetry, okay? So there are some very typical examples of what a group is. So like when you rotate the cube in the 3D shape, so like, in the three-dimensional space, you rotate a cube, then you get many rotations, right? Many rotations. And those rotations will actually gives you a group, okay? You can also like look at hands, you permute them, right? Permute the cards, okay? The permutations, they could also give you a group. And also like, well, when you rotate in that case or flip it over, do the reflection as well, well, they also give you, altogether, they also give you a group. All right, so, but you may notice that, well, okay, this is a set of something, but what is so special about this set that we can call it a group? Okay, think about this. When we have the, like the netness, for example, netness, we rotate it, we flip it. Well, we can actually do the move like keep going, right? So we can just flip it many times, right? Or rotate it as many times as possible. Well, so in some sense, you can actually compose the move. You can do it one by one, right? Do one and do another, like, or the cube, you can actually rotate it along the x-axis, right? Many times. And then you rotate it along the y-axis and keep going, right? So you can compose it, okay? And then you also have a move which doesn't do anything, identity, okay? Don't do anything. It's called the identity move or identity, transformation, whatever, okay? You have something like this. You can also undo the thing, right? When you rotate something, you can actually rotate it in other directions, right? And you get back what you want, right? What you are, right? Get it? So combine these three ideas. All right, formal definition is like that. I'm not going to ask you to like fully understand what's going on with those formal definitions, but I just want to give you an impression that we can use just the rigorous mathematics to formalize something that we have already known. All right. So what is a group? All right. So a group is a set with a binary operation, which means you can combine two things to give you one, and such that the operations has the following conditions. Okay. For sure, you need the operation to be within our set, right? So when you combine two things, it will give you this, the thing we are considering, right? Okay, this is like nothing. The closure condition is trivial. The other three are the things I've just mentioned, right? So like, well, identity. We have the identity, right? Okay. We have the inverses, which means you can undo the thing, right? Yeah. So the identity means you do nothing, right? Okay, you know that. And the associativity, that means, all right, you do the moves and then do the third move. It's actually like you do the second and third move first and then do up. All right, let me put it this way. So I mean, like, it doesn't matter. It means it doesn't matter if you do the GH move, combine it first, and then after that do the K move, or you do the G move and then combine it with or operate it with the combination of H and K move. All right. Yeah. So this part may be a little bit hard to understand abstractly, but when we really go through the problems and when we really see more, examples, we understand more about that. Okay. Cool. By now, still all right, right? Your mind is still here, right? Following me, right? Okay, cool, great. Give me a second. I just want to check if there is. Okay, I see. Great, awesome. So now, all right, for our problems, the groups we really will focus on are those finite groups. So we don't talk about infinite group. Don't worry about that. All right. So you're a CS student, so we are in the finite world. So that means the set is a finite set, okay? And also, the groups we would really focus on are the so-called symmetric groups or symmetry group, all right? Yeah, they're different, all right? A symmetric group may not be a symmetric group, all right? So the symmetric group, the Sn, all right? It's a notation. You should like remember. It's a group of all permutations on n objects. Okay. So you know what this means by permutation, right? Know that, right? Yeah. More precisely speaking, the permutation on n objects is a one-to-one bijection map. Just move the n objects, right? Yeah. Or you can think it as like, well, you have 1, 2, 3, and then you move the 1, 2, 3. You can move it to be like 2, 1, 3, or like 1 to the 2, and then 2 to the 1, and the 3 just don't move it. And then you may also have other arrangement, right? So those are the permutations. Symmetry groups of geometric objects. All right, we focus on the cube and the netlist. But for the netlist, you can actually see it as just a square with 4 corners. Okay, they're equivalent actually, because we are talking about just 4 beats, right? Yeah. So you would say it. So we consider the symmetry over those objects. Okay. So now let's look at them now. All right. I will show you that web app again to get you a better understanding of what's happening here. All right. So the cube. For the cube, we actually have 24 rotational symmetry. All right. For our consideration, we don't consider the reflective one. No. All right. So we can actually reflect it, but you know, in our physical world, it is not possible for you to reflect those cubes. the die, you cannot do that. So we only consider rotational one. Okay, the rotational one. So there are 24 of them. You may not see it, but actually you can see it using our app here. All right. So for the x-axis, you can see that here, 1, 2, 3, 4, and then you will get back, right? Oh, so I'm sorry about that. Okay, let me get back to the original positions. So you can see this, right? And then x-axis, we do it 1, 2, 3, 4, and get back, right? Yeah. So except for the identity rotation, for the x-axis, we have 3 of them, different rotations, right? For the y, we also have 3. For the z, we also have 3. Z, whatever. So, all right. So for the diagonal, let me put it in this way. For the diagonal rotations, okay, we have 1, 2, 3. Get back, right? See that? Don't see this. All right, let me just show you again. All right. So we have the you remember 1, 5, 4 here, right? So when you do this, do this, do this, get back, right? The other 3 are also like this. So each of them gives us, except for the identity, 2, right? 2 rotations. Okay. And then here the edge centers. All right, remember this one, right? And then now you can actually flip it. The 5 just flip it to the other side, right? And then we just do it up. Well, I should just show this one to you. This one is better. Sorry about that. Let me just redo it. We do it. Okay. All right. So this one is okay. Doesn't matter. So the 5 go here, but when you do it again, we flip it back, right? So each of the edge center axes will actually just give you essentially 1 extra rotation, right? So altogether, 6 here. Here is 8, right? 2 times 4. And then we have 9 here, 3 times 3. And also the identity, altogether, 24, right? Okay, if you count it in this way. All right, but it's okay if you still need some time to understand what's going on with those rotational symmetry. It's okay. Just keep it in mind that we have 24 rotational symmetries there for the cube. Cool? All right, awesome. So now let's get back. All right. So you can see that each rotation permutes the faces. All right. So you can see that each of them would not really like fix a face. No. All right. Some of them would. I mean, like they will permute at least 1 face, right? Yeah, I should say at least 1 face, right? So this rotation actually gives us a group, which is called the symmetric group S4. Yeah, so it's basically the permutation group of permutation on 4 objects. Okay. Yeah, this is one thing. All right, the other thing about the hands. All right, poker cards. All right. So now we could think about those 3 hands. We are actually trying to permuting them, right? Yeah. So we have like 3 positions. So for those positions, we can actually permute them like, well, the 1 to 2, and then 2 to 3, and then 3 to 1, right? So in notation, we represent it in this way. This is called a cycle, all right? So that means 1 goes to 2, 2 goes to 3, and then 3 goes back to 1, all right? So all this permutation will just give us a symmetric group, S3, which is the all the permutation on 3 objects. Well, so I will show you more about the notations later, but let's also move on to the square or the lattice. So for the lattice, you can actually think it as like a square. Yeah, so 4 B's, they are just 4 corners. So now you think about the symmetry on it. So basically could just rotate it, right? So 4 rotations. But you also have 4 reflections, okay? The reflections are like, well, across the horizontal line, across the vertical line, or across the 2 diagonal axes, okay? Yeah. But here it actually gives you a symmetry groups, which is called the dihedral groups, D4. All right, so we have like 4 rotations and then 4 reflections. Yeah, you should be able to see it. Okay, so like this. And now, okay, on top of these things, so all right, now we have a kind of like a vague idea what a group is, and what could group do to us for like helping us solving the counting problems. All right, that is another question, right? Now let me introduce you one more new idea, and after that we're going to a very powerful formula, which basically one formula solve all the cases. Cool. Okay, but in order to understand that formula, we have to know one more thing, which is called the group actions. So group actions, you can actually see it as like, well, now we have some group, okay? Like the cube, we have the rotational symmetries. For the card, we have the permutations. For the netness, we have the symmetry on the, the square, which is like on the netness, right? So now we can see that all those things, they are transformations on something, right? We're rotating the cube, right? So the cube is there, but the group is actually the way we rotate it, right? All right. So you're actually doing an action on it, right? So you're using a group to do action on something. Well, that's called a group action. Yeah, certainly this is not a precise definition for the, the math group action, what it means, but well, that's the idea. The precise definition is just like that. All right. So whenever you have a group, you can say that it adds or it has a group action on an other set, X, if we have the following things there. So, well, each of the group element, you know that the group is a set, right? So it has its own elements. So like our rotational symmetry, we have like 24 symmetries there. Each of them will give you a function on the set. So our set here, X, is the cube. This is our set. Okay, it has 6 faces, all right, whatever, 6 faces. And then we have the group, symmetry on the cube, rotational symmetries. And now we can add it. And then the cube will just be rotated, right? And we have to make sure we have the following compatibility conditions and the identity conditions. So that means, well, the identity in our group will do nothing on our set. So it's true, right? The rotational symmetry is there. We have the identity, which means do nothing, right? So the cube will do nothing. Okay, great. The first one, set. compatibility. Compatibility, that means whenever you do one thing there, well, I will rotate it by 90 degrees, and then we can just keep going, all right? But it will be the same as, well, you do that operation here in the group first, and then apply it on the set. So it's just like, well, I can do it like one by one, the x-axis, like we do it once, and then we do the y-axis rotation, okay? It's the same as like, well, you do that xy rotation combined one time, like all for one for that cube, all right? Yeah, so this part is kind of abstract, I understand it, but actually what you really need to know is, well, we have the symmetry group there, okay, and we have the cube there, and then we can pick one thing here, add that on the cube we have, and the cube will be rotated, okay, just like that. So here we have some notations. All right, those notations are just for later use to illustrate that formula. Okay, so that formula is not very hard to understand. Okay, I will explain it, interpret that. But some of the notation, well, you better just remember it. So like orbit of x, we use gx, not no subscript. It's just companion, all right, g and x. That means we are taking all the elements in x such that it just moved by the g from the x. So we fix the x there. We fix the x there, and then we apply different g on the x, and then we will get many other elements in the capital X, the set, right? Yeah. So here we have many things now. Okay, and this gives us a set which is called orbit. Okay, and as far as I know, you should have learned the equivalence relation, right? Equivalence relation, right? Okay, so the orbit is actually an equivalence relations. Okay, so that means the orbit will actually divide the x into different compartments. All right, so now we have like gx1, maybe gx2, and gx3, etc. Okay, so these are the orbits. You can think in this way. Okay. Yeah. So what does it mean by equivalence relation? Do you remember it? Yeah. You may not remember the precise definition. Is okay. Yeah. Just you only need to have an idea that equivalence relation will just divide the set into different compartments, right? They're on their own. Yeah. It's like we divide the whole class into different group of students. All right. When you're in the same group as the other, you're in the same equivalence relation. Well, the grouping thing is equivalence relations. You're in the same equivalence class as your classmate in the same group. Oh, yeah. So all bases like that. And then the next one is called the fixed point. The fixed point is, well, the fixed point of G. Okay, let me be more precise. So when we have a group element, so we fix a rotation, that rotation. And then now we try to find if there is any x that when we apply this G on that x, we'll get that x. If it happens, if it fixes the x, right? So the x will be called a fixed point of G. Okay. So like for our situations like here, you can see that we have 6 permutations here, right? So you can see that some of the permutation actually fix our x there, all right? So x here is the different arrangement of the 3 cards, right? One arrangement, one element in the big X, all right? The capital X. And then now we can see that some of the permutation actually fix that X. So like this one, right? Yeah. The permutation, we just permuted 2 and 3. It actually fixed this element, right? The element here we consider is the 8, heart 8, and then the king of apart, and then, you know, 2 kings apart and 1 8 apart, right? Okay. So if we put the arrangement like the first one is 8 of heart, the second and third one, they are also kings of hearts. Then now, if we consider the permutation that we don't move the 1, but we just swap the 2 and 3, then this permutation actually fixes this element, right? Yeah. So this is called the fixed point of some G. All right. So this is this guy is the fixed point of our permutations 2, 3. Yeah, we can represent our permutation as like this 2, 3. Just we swap the 2 and 3, right? Yeah. So this guy is a fixed point of the permutation 2, 3. All right. Okay. The other two are just like, well, we could have many fixed points for some G, right? So when we just fix in G, we could have many fixed points. We collect all the fixed points, we get a set. This is called the set of all fixed points of G. Okay, we denote it as X and then upper script G. And the last one is the G lower subscript X. So this one is we fix the X and we consider all the G which fix the X. Right? So we're thinking about like in another way. Okay? Yeah, so XG is we fix the G and we consider all the X such that it fixes the X. And the GX is, well, we fix the X and we consider all the G fixing the X. All right? But now, all right, this is not just a set, it's actually a group. All right? I'm not going to prove it to you, but I will tell you, well, it's actually not only giving you a set, itself is a group. Okay? Okay, so now here are some more notations about the permutation thing. So like 1, 2, it means we swap the first 2 positions. The 1 to 3 is just like what I mentioned. We just do it 1 to 2, 2 to 3, 3 to 1. Okay? Yeah. And so now we can see that if we are considering the hands, we can actually get from one hand to another hand by permutation, which I have already shown you here many times. Okay, so like this one, right? So we can get from here to here, but it fixes it anyway. But we can also get this from this one to here to this one. All right, so the permutation here we applied is like we swap the 1 and 2, right? We swap the position 1 and 2. So this is why we get the second one, right? Yeah. So okay. So now we are all set about the the notations, definition, whatever. Now, okay. So this part is the most important part of the whole gas lecture. It's called the Burnside's lemma, or sometimes we call it Burnside's formula. Well, it's actually a formula. So the formula is not this one, but this is the easier version. All right, a special case. Okay, so here we have a new notation now. X quotient G. All right, so we see it as the number of, okay, when we consider the number of elements in this set, okay, we call it the number of orbits of G acting on X. Okay, so like here, if I use this as an illustration, well, you can see that. Well, 1, 2, 3, 4, 5. So when we are talking about the group action on this X, we get 5 orbits here. Then this number, X quotient G, is just 5. Okay? So we're just counting how many equivalent classes are there. Right? Equivalence classes. Okay? Yeah. So you only need to know that, well, equivalence relations give us equivalence classes. So we are just doing something like dividing our class into different group of people, right? And then we count how many groups are there, right? That's it. Okay. Yeah. So this is the number of orbits when we consider the group action G on X. And now if the action is like, well, we do not have any fixed point for the non-identity elements. All right, so let me be more precise here. So if you consider identity elements, the identity will actually fix everything, right? Because you do nothing. You don't even move anything, right? So well, everything is fixed. Okay. So the identity is special. It fixes anything. Great. But now a non-identity element could also fix something, right? Sometimes. We don't know. So like our case for the hen, you can see that. Well, this permutations. The first one is the identity permutation. The second one is we swap the 2 and 3 position, right? But for this case, this is a non-identity element, but it also has a fixed point, right? But now if our case is for the non-identity elements, we don't have any fixed point, then we can calculate the number of objects very easily. We just, well, think about the x, number of x, and then divide by how many are the number of group elements there, and then we get this, basically. All right? So how can we picture it? Well, think about that. You can think about like someday Anderson calls you guy, well, divide yourself into different group of people of five students each group, all right? Okay. Then how can you count how many groups will be formed for this case? Well, for example, if you have like 100 students and you need 5 of them for each group, so basically you will get 20 groups in the end, right? Yeah, assume you're like, fair and, everyone not hating each other. So, so all right, 20 groups, right? So this idea is just like that, okay? The number of elements in the X, number of people in the classroom, we divide them into different group of people. How many groups are there? All right, we just look at how many people for each group, right? All right, so we do a fair trade. Well, 5 people each group. Okay, great. So 100 divided by 5, we get 20 groups, okay? Well, but the thing is, we don't always get this, right? Yeah, this is called the fixed point free case, but many group action is not fixed point free, okay? So just like our second question is not fixed point free, obviously, because we have some non-identity element, which, gives us some fixed point, all right? So we need a more sophisticated formula to deal with this. Burnside's formula, okay? This is the formula, which is the more general one, okay? So basically the interpretation here is, well, for each symmetry, for each group element, we try to count how many objects are there, look unchanged under this, okay? So we are actually counting how many fixed points for the G, all right? And then we sum of them, okay? For each G, we do this, and then we take the sum of them. And then we average this over our group. So like our group has 10 elements, say for example, and then we divide by 10, okay? And this will give us the number of objects. Okay, so it may be not very easy for you to understand what's going on with that, all right? And I'm going to show you the idea of the proof, not necessarily to understand that. So this is the idea of the proof. You can skip it, but I will still just talk about that anyway. Well, so the trick here is, how can we prove it? Well, we use something to connect them. It is like a very traditional mathematics, a method of proof. We use a bridge. Okay, the bridge here is the C set. What is that? Okay, the C set is actually all the pairs of G and X such that when you consider the actions, it affects the X, okay? So we will have like many pairs there, okay? For the C, we don't fix X, we don't fix G, we consider all, okay? Yeah, so whenever we have a G fix X, we take it and put it here as a pair, all right? So for one X, there could be many G, which pair with it, right? So we have many pairs for the X, it could be. And for G, we also could have like many X pair with it, which gives us the fixed point, right? So, well, the set is like this. And now we try to count this set in two ways. The first way is, well, how about we fix the G and count how many X fixed by the G. And for each of them, we count them, all right? And then we take the summation of them. And it will give us the number of pairs like this. Okay, this is one way. The other way is, well, now we don't fix G, we fix the X and consider how many G's are there fixing the X. And now we go through all the X. We get the same thing, right? But for the second one, we can even further do it in a way like, well, we consider each orbit. We go through those x1, x2, xn, whatever. Okay, we go through them, the I summation. And then for each orbit, we just take the summation of the number of elements in the group fixing the X inside the elements in this orbit. All right. So it's like, well, originally we just go through those X one by one. And for each of them, we consider GX. Now we don't. We go through each orbit. We fix an orbit. We go through the orbits, goes like this. And then we go to another orbit. All right. And so the inner sum is just here. We are summing over the elements in that orbit of the number of the number of group elements fixing the X. But we have another property which I'm not going to show you here, sorry about that. But it's more like it's a very basic group theory thing, which we can show that for each of the elements inside the same orbit, the number of elements fixing the element is the same as the representative. So for each orbit, we can actually pick one guy to be the representative. It's just like a very traditional equivalence class treatment, all right? But, well, for the other guy inside the same orbit, then those guys actually basically share the same group of fixed point with the representative. So now for the inner sum, all those GX are actually GXI. All of them, they're GXI. And now you take the sum over that orbit. So the number of elements in that orbit will be the number of term like GXI there. All of them are GXI. All of them are GXI. So now if your orbit has like 10 elements, then you have 10 GXI term there. So like your GXI may be 3, then you have 10, 3 here, right? And the 3 plus 3 plus 3, you have 10 of them. All right, so the inner sum is like this. Okay, yeah. So now, this guy will actually give you back the number of elements in G. So now, eventually, you will have the sum as sum of I and G. But remember this sum, the outer sum is summing over the number of orbits. So actually now you have like X quotient G number of, the bar, well, the absolute G term here, all right? So this guy, I call it like whatever, alpha, okay? So now how many alphas do you have here? All right, so you have exactly the number of orbits, I call it as K, all right? So the number of orbits, I call it as K anyway. So you have K alpha there, all right? So now you can see that the K alpha is just that original sum, and you just move that alpha over there, which is the number of elements in G, then you will get your formula, okay? So this is kind of like, a combinatorics done using the good theoretical sense. Well, anyway, so that's just the idea. The actual proof is much more than that for sure, All right. So, but this just gives you the idea that, well, when we would like to prove this formula, we can actually just, do it in this way. All right. So finally, how can we solve those three problems? Easy. So the first one is very easy. I've already told you that the rotational symmetry, we only have like 24 of them. Okay. And now what we need to do is, well, we already have the absolute G, right? 24. How about the absolute X, the number of elements in X? Well, the number of elements in X is an easy problem for the counting problem, right? You just count how many ways you can put the numbers, onto the cube. So you have 6 choices on the first phase, and the second phase you have 5 choices. For example, like just keep going. You will have 6 factorial in the end, 720, right? So now this case is a fixed point free case, because if you look at our web app here, you can see that every one of them will at least move one phase. All right. Some of the phase may be fixed, but at least it moves one of the 6 of the phase, right? So it cannot really fix anything for those except for the identity, right? So now you can see that it's a fixed point free case. So we just divided 720 by 24, get our answer, 30. Okay, we only have 30 distinct dies up to rotations. All right, second one. Second one is the 3 cards case. So now we can think about our 3 cards set as like A1, A2, A3. They're representing like different suit and numbers. All right, so you can think it as like, because we have 3 that's combined together, right? So the A1, A2, A3, they're from like 1 to 52. We just label them as 1 to 52, right? We have 52 different cards. So the number of elements in this set is just 52 to the power 3. Easy, right? And I've already told you that we're doing permutation. So basically the group of our interest is S3. So okay, the problem is, what is the absolute S3? All right. So what is the number of elements in the S3? Okay, easy. It's actually just 3 to the power 3 factorial, 6. Actually, you should know it here, 6. Okay. But the next question is, well, are there any fixed point? Yes. Except for the identity, we still have other X fixed point. So say, for example, the 1, 2, we're swapping the positions 1, 2. We have some fixed point there. How many fixed points are there? Well, whenever the first 2, they're the same, and then it fixes it, right? So we actually, for this one, we have 52 square cases, which the 1, 2 can fix it. Similarly for the 1, 3, and 2, 3. And then we also have 2, 3 cycles. So we can just go from 1 to 2, 2 to 3, 3 to 1, or 1 to 3, 3 to 2, and 2 to 1. All right. So these 2, 3 cycles, they also just fix the cases, which all the hands, they are the same. So basically for each of them, they fix like 52 arrangement only. Okay. So in the end, we just put all those numbers together, right? So we have the identity, which fix everything. So 52 to the power 3. Okay, adding the the number of fixed points for each of these guys. So we have 3 of them, and then finally we have 2 of the 3 cycles fixed point. So do the calculation. We have 24804 cases there. Okay. Yeah. By the way, we actually have another way to do this. If you know the multi-indexes, yeah, you can use a quite combinatorial way to do that. Yeah. But I always see the group theoretic way more like beautiful. Okay. The last questions. Yeah. So now we think about the netness. Okay. 2 black bees, 2 white bees. Okay. So we have the group action on it, which is the D4, right? I've already told you we have like 8 elements there only, right? The absolute G, right? So now we use the Burnside's formula to count it, but we have to know if there are any fixed point, right? Yeah, the identity fixes all the point for sure. Okay. But now we think about it. Well, in 1, 2, 3, 4. So that means we just rotate 90 degree, rotate 90 degree. It has no fixed point, right? It would not fix any arrangement because, well, you can think about it, right? So like here. Okay, rotate one time. Even if you have different types, it still just moves something, right? It would not really fix anything. Also, if you rotate it by 270 degree, it would also not fix anything. And then for the other, like the 1, 2, 3, 4, like this one is actually like you are reflecting the 1, 2, 3, 4. You're actually reflecting like this, right? So here, you're reflecting along this axis, right? And then it will actually fix something, all right? It will fix two cases, all right? 2 right, 2 black, or 2 black, 2 white, right? Similarly for the other 2, 1, 3, 2, 4, or 1, 4, 2, 3, all right? And finally, the 1, 3, and 2, 4, that means you're doing that reflection like this. You can see that both of them will also have 2 fixed arrangement. So altogether, we use the Burnside's formula, then we will get this thing. And finally, we actually have just 2 distinct lattices. As you can see, you know that. 2 of them is like 2 white, 2 black. The other one is like alternating. Yeah, just two of them, okay? So that's it, actually. Done, right? Yeah, sorry about that. A little bit over one though. But, well, so you can see that from this guest lecture, well, the symmetries can cause, severe overcounting if you don't consider them. So when you take them into account, if you use the combinatorics way, it may be very difficult. But now if you introduce the group theory and use the Burnside's formula, then everything is really, easy if you use that formula, right? So for the CS and AIUs, there are actually many uses if you, just use the same idea. So like, well, in CS or AI, you may see sometimes you may see the graph automorphisms or isomorphism thing, or like the symmetry reduction in the searching and panning, or the invariance or equivariance in the machine learning models. There may be some, symmetries, which you can actually count how many paths there by, Burnside's formula if you can just construct the group actions. Okay, so these are the references, and now it's done. Okay. All right. Yeah. Thank you very much for joining this. And that's it for today. And if you have any questions, you can just ask me. Okay. Yeah.